2 tests about a population proportion. We're looking at significance tests, which are a formal procedure that compares an observed data value, some statistic that you just measured, comparing it to some claim, also called a hypothesis, that we feel is the truth. Here's your sampling distribution, and you're wondering if you have enough evidence to reject your claim of the mean or the parameter that the parameter, which could be a mean or it could be a proportion that you think is in the middle. So when you're planning your studies, you're going to be looking at significance level, like how much protection do you want from type 1 error? We talked about type 1 error last class. Type 1 error is when you have rejected the claim, rejected the null hypothesis, and if that null hypothesis really was true, you've just rejected it and you have now made a mistake because you have just said that the null is false, and in fact it was really true. That would be type 1 error. So what's the probability that you want to have that happen? Then practically, how much difference do you have between your hypothesized parameter and the actual parameter? It's going to be important in like what you're working with. And the power, like how confident do we want to be that if we should be rejecting this null, what's the power, what's the probability that you want that you need that to happen? So basically, if you look at this table right here about the different situations, if you want a low alpha, alpha being the same as type 1 error, alpha is the probability of your type 1 error. If you want to improve this, you want strong evidence to reject your null, meaning you need to have a lot of data, then increasing your sample size is going to help you do that. If you want high power of a test, if you want low beta or low type 2 error, then you're going to have beta being the probability of type 2 error. Means better chance of detecting differences between your hypothetical and actual parameter values. You're going to increase your sample size to see the differences. Okay, great. Another thing where you increase sample size, heard that before. And if you want a small difference between the actual and hypothetical parameter values, and a small difference that can be, these can be much harder to see, like if there's really is a small difference between what you're getting and what the real value is. Increasing the sample size can help you see those small differences. So clearly, increase sample size is a great way to improve your studies. Okay, the moral of the story is use your highest type 1 error that you can tolerate and the largest sample size that you can afford. Here's a summary of the probabilities. Probability of type 1 error is alpha, probability of type 2 error is beta, and the power of the test is going to be 1 minus beta. We'll look at that in future pages. Okay, so next page, we're going to be doing a one sample z-test for a proportion. The z statistic is approximately has approximately the standard normal distribution when the null is true. Our p-values therefore come from the standard normal distribution. So here's our test statistic right here. Our z is going to be, and we have our statistic that we just measured from our sample. We have our parameter value. That's what we are testing. We think that it might be true. We're going to assume that it's true unless we can find evidence to the contrary. And then down here, we would have our standard deviation of our sampling distribution. Notice there is no hat on these symbols, meaning that what we are thinking is the parameter value, that's what we're going to be doing for our test. Now it's interesting, the new formula sheet for the AP Stats test, the new formula sheet calls it standard error if you look at the formula sheet for this, but they have a little asterisk on it. And that asterisk does say that you're going to use the standard deviation of the sampling distribution when you are assuming that that's true. So it's going to be really important that on intervals, you're going to use the hats, but on tests, if available, you're going to be using no hats, you're going to be using parameter values. Okay, this shows you the different kinds of tests that you can do. Confidence intervals are a two-tailed situation. So confidence intervals are related to this situation, but in a test we can be checking situations where our statistic was higher. We can check it if it's lower, and that would be a test. But this one is related to confidence intervals because it's two-tailed and like it looks like confidence intervals. Next page. Okay, so when our conditions are met, still checking the same conditions. We need to be random, we need to be normal, we need to be independent. Then the sampling distribution of our p-hat will be approximately normal with a mean of, and then these are off of our formula sheets. You can see them on the formula sheet. These symbols, I like to write my symbol with Q just because it's, just like to do that. So when performing your significance test, make sure that you are looking at P, as I said. Okay, looking down this page. Okay, so basically we are doing significant tests, uses the sample data to measure the strength of the evidence against the null, because you've basically assumed that the null is true, and now you're looking, although you should never say that you think the null is true, we are going to assume that it is, and we're looking for evidence against it. The test is going to compare that statistic calculated from the sample data. It's going to compare it to the parameter that you've stated in your null hypothesis. And then if we can find enough evidence, if our p-value, that's our evidence, our p-value, if we can find enough evidence that it's typically we use 0.05 when it's not given to us. If our p-value is below that, then that's giving us an indication that we have enough evidence to reject that the null is true. Okay, here's on your formula sheet right now, the new formula sheet, they call this the standard error, but that's just because you don't always have a population value, a parameter to use. But if you have a value that you're testing, if you're saying that your mean is, if you're saying that your, sorry, in this situation we'd be using a p because we're doing proportions. If you're saying that your proportion is 0.2 and your p-hat was maybe 0.23, like this is the one you're going to be using. On the AP formula sheet, you'll see a little asterisk. They tell you that if you have the value available, you should be using the population parameter. So that's what we're going to be doing. So let's go through and see if we can do this example with our basketball player shooting, telling you that he is an 80% free throw shooter. And he just went out there and got that 0.64. We looked at this last class and we're looking at it again. So first of all, make sure that you've defined what you're talking about. So P is going to be the proportion of baskets made. So he says that he's an 80% free throw shooter. So I'm writing down that he said that. And that's my parameter because he's saying that's the truth about him. But he goes out there and on this day, he ends up shooting a .64. So that's our statistic that we're going to be examining and testing to see if this is true. So random. It was given that was an SRS. So that's good. We've met the random condition. We need to meet independence in order to be able to work with our standard deviation of our sampling distribution. We would need to have independence. So he's taking 50 shots. So that's a good thing. But this doesn't really apply in this situation. This would be our usual check for finite things, but this actually doesn't really apply here, although you can still use it. But really, free throws were independent, weren't they? Each time he shoots, he's getting a new chance to make that basket. Now, next thing, nearly normal. We got to meet that condition. These are all our conditions of inference. So to be able to do that, we need to have our N and our Q. And notice that I have not P hat, I have Q and P. I don't have the hat on there. So that means that this test is going to actually be with our parameter. So there you go. I put my parameter in there and I want it to be greater than or equal to 10, and 40 definitely is. You know, each textbook has a different level. Some textbooks even say this can be as low as 5 before they can do that. But anyway, this looks good. Just made it. So we are meeting the nearly normal condition. So since our conditions are met for inference, I would like to do, I'm going to slide this up so I can write it. I would like to do a one sample Z test, not a Z interval, but this time I'm doing a test for a proportion. It's really helpful to know what your tests are called because then you can use your calculator to check all your answers, because if you know what the name of the test is, you'll be able to find it under stat tests and you can do your tests in there. All right, so I would like to write my hypotheses. I'll put them up here. I would like to test my null hypothesis, my alternative hypothesis. Sorry. I would like to test that, well, he said he could shoot 80%. So I'm going to give him the benefit of the doubt, and that's the null. But I'm interested in, let's see what we're interested in. Are we interested in him being higher, lower, or just different? In this situation, we're wondering if he's lower. To me, that seems to be like, if here's my parameter, which would be the middle of my normal curve, he just shot this, and I only care about him being lower. I don't care about this side. That would be if I wanted him to be different, I would look at both sides, but I'm just wondering if he's actually lower. So I'm wondering if he really is below 0.8. See, same value, same P, statement of equality in the null, inequality in the alternative. Okay, so now I've got to find my Z-score. And well, in order to do that, thank goodness I was independent because I can find my standard deviation of my sampling distribution using parameter values. Throwing those in there, and I get 0.0556. Yeah, lots of decimals because you don't want to have any rounding errors. And so now I go to calculate my Z-score, and as it says on the formula sheet, the statistic goes first minus the parameter. Then that standard deviation of the sampling distribution is going to be my denominator. And I get negative 2.828. So there's my z-score that will then be going into my, well, normal CDF, as you know, but I don't write that on the test. I don't want anybody to know that I was not using my table. So here's my p-value. I just found the p-value that is my evidence. Because it's so much lower than 0.05, that's some good evidence that this guy, I can reject the null, and I'm really thinking that he does not shoot 0.8, that he's probably lying to me. So since the p-value, because everything's got to be written in context, so is less than, so since the p-value of 0.00234 is less than alpha equal 0.05, we reject the null hypothesis and there is significant, I can use that word significant because I actually did some math, evidence, not substantial, that's when you didn't do any math, you use substantial, but significant evidence that the basketball player shoots lower than 80%. I don't think he's a 64% shooter. I just know that this evidence that I have, because every time you go out for a statistic, you're going to get a different value, but I know that this particular time he got that, and right now it looks like we've got evidence saying that he's worse player than that. Now, describe the type 1 error in this situation. So, if this is his curve, this is all the 0.8 basketball players in the world. They're all on here shooting. This is him shooting as a 0.8 basketball thrower. And really, this area out here, he's still actually part of that curve. He's still really part of that. But that was my alpha. That is my type 1 error. Because he's really on that curve, and I just think that he's lying to me because he's having a really, really bad day. So, you know, basically what's the context of this situation? If I really did commit type 1 error, the context would be he is an 80% thrower. I didn't realize it. It, and I thought he was lying. Because he's having that bad day, and I just accused him of that. So that could be a problem. So if we look at this situation, like, okay, let's say that he really isn't an 80% basketball player. So this is going to be a little bit complicated. We have to kind of take this piece by piece as we kind of look at what's the type 2 error, what's the power of the test, the probability of type 2 error. Those can be more difficult situations to understand. Now, the main thing in the AP test is they're going to want to know that you can tell that your beta, which is your probability of type 2 error, that along with the power will equal 1. So, you know, your power plus your beta will equal 1, because that's going to be all the situations. This is basically you catching the guy, caught the guy, the bad thrower. And this is you with the guy having a bad day, but you just made a mistake. You told him he was a terrible thrower, but he really was a great 0.8 thrower, just having a really bad day. So those are the two situations that can happen. So here's my sampling distribution for the 0.8 right here, as you can see right here. That's him being that thrower. Now, let's say, if you look down below, it says, let's say our basketball player really isn't a 0.8 thrower. He's a 0.7 thrower, 70%. So what I like to think about is, okay, where would 70% be? Right around here, maybe, something like that. This is where 0.7 is. Now, think of this as like he's walking among us. He's actually part of a different curve. This is the 0.8 curve where the 0.8 throwers belong, but he's not really part of that curve. He's part of this other curve. But as you can see, there's a lot of area in here where there's this overlap where you can see, and this was his day right here. He just had this day right here. He just threw like that. So, you know, a little bit, he was having a little bit of a bad day, a little bit below what he normally would do, but he's way below what he's claiming. So this being our initial claim, and we're trying to compare this value to that. Now, if I look at, if I want to look at where on this first curve, let me use a red to like trace. Here's him being this 80% thrower. What I want to look at is I want to look at, well, where would I start rejecting someone? Where would it be? Here? Would it be here? Here? Where am I going to start rejecting someone? Because I know I rejected at 0.64, at our statistic of 0.64, we rejected the situation of him being that kind of a thrower. But let's find out, where would I reject someone? What value on the number line down here would give me an area of 0.05? What number would that be, would he have to shoot in order for that to happen? Let's find out. We know that we are assuming it's a 0.8. We had our standard deviation of the statistic from the last page. We had that value. We know it was this right here for 0.05656854425. Whoops, that was a little annoying. We know it was that, and so let's just, for the heck of it, I'm going to write some calculator speak, but all right, normal CDF. Oh, wrong command actually, because I want to get the X value on that line, so inverse normal. I want a 0.05. I want to know what point would he have this happen? 0.05, now I got to put in the mean, 0.8, and I got to put in the standard deviation right there. So I'm going to put that into my calculator. 6 ... with all the numbers that I would have had. And I put that into the calculator, and it just jumps out with, it gives me punching that in, 0.70695. Okay, back to our curve. It looks like if he was having right here, around here, so if he was having a perfect day, he'd actually be below our number that we would start saying that somebody was lying to us. This being if he's really part of this curve, right? The area of that, if he was really part of that 0.8 curve, that would have been our type 1. That green area that you see right there. But what we just said. He is not a 0.8 thrower. He is really a 0.7 thrower. So let's look at where 0.7 is right here. This is 0.7. Well, it's supposed to be in the middle of my curve. Not the best drawer. But moving up, he's a 0.7 right here. Okay, this side, right there in blue, that's my power. I caught this 0.7 thrower, and that's the area below my test value that where I'm catching him. Whichever number was on that side, I would be, since it's a 0.7's on the left side, that's why I'm going to use that value. And then if you think about it on this side of here, this is my power from here. Sorry, this is my power from the value of this. This is my power, because below that I was going to reject the claim, so that's my power. And then on this side I would have made a mistake, because on this side, he's really part of this curve. Here he is in this curve. But if it was on this side, I would not have enough evidence. Remember, on that side of the line, I'm going to reject him and know that he's not a 0.8 thrower. On this side, I'm going to fail to reject him and not have enough evidence to reject him. But remember, he really was on the blue curve. He really is a 0.7 thrower. So that would be our type 2 error. Now, highly, highly, highly unlikely that the AP test is going to ask you to find the power of the test in this situation, but we can do it. I'm going to write it in calculator speak just to kind of explain. So we're on that blue curve, and he's really a 70% thrower. So our power, if I want to find the area, I want to find this blue area up here. This blue area at the top here, I'm trying to find this blue area there. Okay, normal CDF. Okay, but what am I going to put into this? Okay, left, right. Okay, so my left one, I say something really, really low. I mean, of course, that's never going to be negative 10 in a proportion. Okay, left, right. Here's my right side. This number right here, this is what I'm putting in the right, 0.70695. Remember, that was the point where I'm going to reject. Left, right. Now I got to put in the mean. What did he say he is? What's the mean that he is? He's a 0.7. I'm trying to find the power to catch him, the 0.7 guy. What is his standard deviation of his statistic? Well, I got to find that value using what we know to be true about him. So using what we know to be true about him, and I'll put that number right here, 0.064807407, I need to find out the probability of that blue area. And so I get, for that, I get a power of 0.543. So that's my power. If he's really a 0.7 shooter, that would be the power of me actually catching him. So what if he's not a 0.7 shooter? What if all that was wrong and he really was a 0.8 shooter? Well, then my probability of my type 2 error, which this is the kind of calculation that you can really expect to be on there, especially in the multiple choice, where they give you the power, and then they just want you to find the type 2 error. We know that those two things have a relationship, 1 minus the power, is the probability of your type 2 error. So in our situation, we have 0.543. So my probability of making a mistake of that kind, type 2 error type, would be 0.475. Well, we'll have time to video chat about all this stuff. Good stuff right here. All right, but main concept being that you want to understand that relationship between those two, the power, the type 2 error, knowing what the type 1 error is, knowing that increasing your sample size can really help solve most of your situations. It's a good answer to put. All right, so let's do a two-sided test example because that's going to be really related to our confidence intervals. So according to the Center for Disease Control and Prevention, we have that 50% of high school students have never smoked a cigarette. That's talking about the population because it's coming from the Center of Disease Control. So they're saying that that's the big value, parameter value. But we go out and we take our sample at a large urban high school. That's good. That's going to help our independence. We go out and we find out that really they got at this high school this one particular time. Every time is going to be different, but this time they got a 0.6. So we're wondering if our school is different, higher, lower, different than national. So check our randomness. It was given that it was an SRS, so that's fulfilling that. Is it independent? In this case, unlike with the basketball shooting, this case we have a finite number of people on the planet, so there's a finite number of people. You really have to do this check. And so N equals large high school, so large urban high school, so that is going to fulfill that condition. Nearly normal, checking it with P, not P hat. Checking it with Q, not Q hat. We're going to be using our parameter values here because they're available. If they weren't available, then we wouldn't be able to check them, but we're checking them with those parameter values. That's kind of convenient that they are both exactly the same 0.5. So we have that's good. They both are doing that. So that is good. So I will say because they didn't specify a level of significance, I'm going to specify the 0.05 significance level, my favorite one. And since my conditions are met, therefore, I name my test so that I can know when I want to check myself using my calculator, I will say that I'm doing a one sample z-test for proportion. And now I just need to write my hypotheses and carry on. So we were looking at this situation. In the middle, we have our parameter right here, and we went out there and got that statistic, which of course would lead us to this tail on our normal curve. But since we were testing difference, we're also going to have to look at the lower side as well. So let's write our hypotheses that we're going to be testing. Okay, so our parameter, statements of equality in the null, and there's my parameter value that we're going to assume is true, and we are looking for the two-tailed situation where it's different. So that's why I have both tails, and that's we're going to have to double our p-value at the end to make sure we get the right probability. So find our standard deviation of our sampling distribution. Since they're available, I'm going to use parameter values because I'm doing a test about the parameter, and therefore I need to assume that my parameter is correct. My z statistic minus parameter over my standard deviation of my statistic. Make that a little longer, 2.4495. And so now I have my z-score that I'm going to then put into my calculator, although I'm going to write it with nice notation that I'm looking for my z being greater than this 2.4495. Because if you look at the original curve going up, this is what I'm finding right here. This arrow here, I'll color in green so you can see the difference. That's what we're going to try to find right now. We're going to have to double it because this is two-tailed, but that first step, of course, is to find one of the areas at 0.0071943, but then I've got to double it. So let's make sure we double it because like we're going 2 and 0.014336 there, and I'm done. So we had decided to do this test at the 0.05 level because they never said what level they wanted to do it at. So we're gonna do it at that 0.05 level. So conclusion and context, since the p-value, remember this is finding a p-value of 0.0143 is less than 0.05, we reject, just going to put reject in the same word, the null hypothesis, and there is significant evidence to reject the null hypothesis and significant evidence to oh, dang it, I just wrote the exact same twice, but well, don't know how to pause this thing. Significant evidence that the proportion of smokers at school is different, because remember we were looking for different than the national 0.5 level value. Okay, so there you go. That was the test for the proportion. Okay, so then that was a test. Test is basically you've got your parameter, you've got you're testing a statistic that you got, and you're going to either reject the null or you're going to fail to reject the null, and then you would not have significant evidence to conclude that the alternative was true. But why do confidence intervals actually give you more information? It's because, you know, instead of just making a decision, I'm going to reject this, I'm going to not reject this. Remember, we never accept something. The confidence interval gives you a window of maybe some reasonable values that might have been the true value. Now we know we either caught the true value or we didn't, but if I go out there and do many confidence intervals, some confidence level, some percentage of those confidence intervals will have caught that true value, which is a fixed value, not changing. And some percentage of them at alpha will not have caught them. But so here he is, he goes out to this high school, and here's the same exact situation with the 90 students who never smoked a cigarette out of the 150 surveyed at his high school. Remember, we have our conditions were met. Of course, if I was doing these conditions with just this data, I would have been using my P hat and my Q hat, because I wouldn't have had the P and the Q. But if you have P and Q, you're going to check your conditions using those. But since I'm doing a confidence interval, then I need to be working with the standard error, the statistic. So, on my formula sheet, that's not the symbol that I see. I see this symbol for the standard error, the sampling statistic. I frequently write it like this, but hey, free country, right? But that means I need to be using hat values in my formula. So my standard error of my sample statistic in this situation, using the, well, remember p hat of 90 over 150, we got that on the other page, it was 0.6. So using that value in here, 0.6 times 0.4 over 150. Okay, take the square root of that whole thing, and comes out to be a nice number, 0.04. Interesting. So my confidence interval, which takes a statistic, remember, confidence interval is using that data that you just went out there and used. What do you think is reasonable based on that one particular statistic? Every time you go out, you're going to get a different statistic. Oh, my alpha was 0.05 level, so my critical Z is a 1.960, favorite number there. So based on this critical Z value, based on my standard error, I get a window of 0.5216. Remember, this is a window estimating, best estimate of my parameter. Notice how I'm using a parameter symbol in the middle. And then you would want to look, was 0.5 the value from the government, CDC? Was that captured? Was it captured? No. No. And when you make your conclusion, you would need to say the number that you're looking at. You would have to say the numbers you're looking at that you're comparing it to, and that since 0.5 is not captured by the interval of 0.5216 to 0.6784, therefore, I would not believe that his high school was the same as the national average. The national average was not captured by the interval from his high school. So that's what I would conclude there. And so just in summary, looking at this situation, you can see the graph here where we've got our values of p hat that we could get all along this situation. They can be anywhere along here. Every time we go out, we get a different value over and over and over again. But the true value was right here in the middle. Hopefully we're going to capture it. But remember, p hat can show up anywhere. And like maybe it's going to get captured, maybe it won't based on our rejection region. And so we look at that. And so I'll let you read the rest of this and hope everybody's doing well. Talk to you soon. Bye.